Welcome back, everyone. Today we are doing a deep dive into something that, well, it sounds a bit like science fiction at first.
It really does, yeah.
Because usually when you think about calming down really extreme, unmanageable aggression, like medically speaking, we picture a sort of chemical sledgehammer.
Right, a blunt instrument.
Exactly. If an animal, or, a human for that matter, is just absolutely raging, the traditional pharmacological approach is essentially to crash the entire system.
Yeah, you just shut it all down.
Right. You turn the dial on aggression to zero, but you also take out their personality, their cognitive processing, and their ability to communicate in the collateral damage.
Which is the classic hallmark of traditional sedatives and tranquilizers. I mean, historically, neuroscience just hasn't been particularly good at separating the neural circuits for being angry and aggressive from the circuits for just being awake and socially interactive.
Wow, so they're kind of tied together.
Historically, yes. We tend to just blanket the central nervous system with a depressant, and that gives you that classic apathetic zombie-like state.
Which is exactly why this May 2026 article by Adrian on technoscience.net is so compelling. It's covering this breakthrough study from Frontiers in Behavioral Neuroscience.
Really fascinating piece of research.
Truly. And our mission today for you listening is to unpack this naturally occurring compound that seems to act as this highly precise surgical volume knob for aggression.
A volume knob instead of an off switch.
Yes. It dials down the fight, but completely spares the conversation. And the compound doing this, it's psilocybin, the active prodrug in over 200 species of magic mushrooms.
And we should probably clarify right away that we are not talking about high-dose psychedelic trips here.
Right, no hallucinating fish today.
Exactly. The researchers were looking at incredibly low doses, basically microdosing and mapping its potential to selectively calm really exacerbated baseline aggression in a vertebrate model.
And that word, selectively, is doing a lot of heavy lifting.
Oh, absolutely.
I definitely want to get into the actual neurochemical mechanics of how that works. But before we look at the chemistry, we have to talk about the test subject.
The grumpy fish.
Yes. Because, I mean, if you're trying to prove a drug reduces innate aggression, you can't exactly test it on a golden retriever, right?
No, they're way too nice. You need a baseline of just pure, unadulterated hostility.
So, enter the mangrove rivulus fish.
Right. It's this tiny amphibious fish that lives in mangrove swamps, and it often has to survive in these isolated muddy crab burrows when the tide goes out.
Which honestly sounds like a completely miserable living situation, so I kind of get why they're angry.
Yeah.
But why is a fish from a mud puddle the perfect scientific model for this?
Well, it all comes down to evolutionary pressure. Because they live in these highly constrained, resource-poor microenvironments, they have to be fiercely territorial.
Like fighting over every scrap.
Exactly. Their baseline temperament is dialed to maximum aggression just to survive. If another fish enters their space, the escalation is immediate. It's intense. So for neuroscientists, this fish provides an incredibly consistent behavioral baseline. You don't have to wonder if the fish is just having a bad day.
Yeah.
Its entire existence is a bad day.
Okay, that makes total sense. So they have their highly aggressive model. But if I'm playing devil's advocate here,
Sure.
you're dropping psilocybin into a fish tank. How do we know the researchers aren't just getting a fish that is tripping so hard it just, forgets how to fight?
That's a great question.
Right. Because if a fish is heavily hallucinating, of course it's not going to attack an intruder. It might just be staring at the gravel thinking it's the center of the universe.
Yeah, and that was the exact methodological hurdle the study had to clear. To prove selective reduction of aggression, they had to design a test that isolated the actual physical motor escalation of a fight from the cognitive recognition of a threat.
So how did they do it?
They used a highly controlled setup. They put a subject fish in a tank and separated it from a stimulus fish like an intruder with an opaque divider.
Okay, let me guess. They just lift the divider and record the ensuing chaos.
Pretty much. They wait exactly 5 minutes for the subject to acclimate, lift the divider, and meticulously document the baseline interaction. They look at, how fast does the subject react? What specific aggressive postures does it take?
Right.
Then, 24 hours later, they take that exact same subject fish, expose it to a low dose of psilocybin dissolved in the water for exactly 20 minutes, and then repeat the encounter.
See, that is so clever. Using the exact same fish for both the baseline and the variable test, it's like a before and after reality show setup.
It really is a repeated measures design.
Because in a lot of poorly designed studies, you see researchers comparing, like group A to group B. But animal behavior has massive individual variability.
Oh, huge. You introduce so much statistical noise the second you use two different individuals.
Exactly. If they use two different fish, someone could easily argue that fish B was just naturally more chill than fish A.
Right.
By comparing Tuesday's behavior to Wednesday's behavior in the exact same fish.
You completely control for individual disposition.
Right. It proves the chemical caused the change.
Yes, it isolates the variable perfectly. The only difference between Tuesday and Wednesday is that 20-minute psilocybin bath.
Okay, so what actually happened on Wednesday?
Well, the behavioral shift they recorded was incredibly specific. The overall movement of the fish decreased, but the massive, statistically significant drop was in a specific kinetic behavior called bursting.
Bursting. Let's define the mechanics of that for everyone, because this isn't just swimming quickly, is it?
No. Bursting is a high-energy, sudden surge. It's a biomechanical escalation. Imagine the fish rapidly darting toward the intruder and then stopping just short of physical contact.
Like a fake out.
Exactly like a fake-out. In behavioral ecology, this is the physical manifestation of winding up for a strike. It is aggressive posturing pushed to its absolute kinetic limit.
It's basically the equivalent of someone jumping up from a table, shouting, and aggressively getting right in your face without actually throwing a punch.
Spot on, and it's incredibly energy intensive.
And probably risky too, right?
Highly risky. Bursting consumes a massive amount of metabolic energy, and it dramatically increases the chance of physical injury if the intruder decides to just call the bluff and strike back.
Makes sense.
So, post-psilocybin, this specific, highly volatile, bursting behavior just plummeted.
But wait, this brings us right back to my earlier pushback.
The zombie question.
Yeah. Did the bursting drop just because the fish was sedated? Like, did it just tune out the social situation entirely?
And here's where the data gets super fascinating. The fish did not become apathetic. Really. And we know this because another distinct behavior, which they call frontal displays, remained completely untouched by the drug.
Walk us through a frontal display. How is that different from bursting?
A frontal display, or frontal parade, is a cognitive social evaluation behavior. The fish positions itself to size up the intruder. It maintains visual contact, signals its own presence, and evaluates the social hierarchy.
So it's staring them down.
Yes, it requires intense focus and visual processing, but very little kinetic energy.
Okay, so the optical processing centers and the social recognition circuits are fully firing.
Completely.
The fish knows there is an intruder. It is actively evaluating the threat.
The cognitive awareness is fully intact. What the psilocybin did was specifically decouple the cognitive recognition of the threat from the motor escalation of the attack.
Oh, wow. Okay, think about the brain's aggression pathway, like the engine of a car.
Okay, I like this.
Traditional tranquilizers essentially cut the fuel line entirely. The engine stops, you can't drive, but the radio dies, the power steering dies. The whole system just shuts down.
Right.
What you're describing with this psilocybin intervention sounds more like installing a governor on the engine.
Yes.
You can still turn the car on, the radio works, you can still steer, meaning you can socially evaluate the intruder, but the governor physically prevents you from redlining the RPMs into an actual attack.
That is a brilliant analogy, and I'd actually take it a step further. It's not just capping the RPMs, it's specifically preventing the transmission from shifting into combat gear while leaving the sensors completely online.
Wow.
The frontal displays prove the fish isn't heavily hallucinating or dissociated. It is present in the conflict. It simply isn't triggering the costly motor actions.
Which forces us to zoom out to the biology. How is this actually happening? What does this fish's brain have in common with ours?
A surprisingly large amount, actually.
Because we know psilocybin is a prodrug, meaning the body metabolizes it into the active compound psilocin.
Yeah.
And we know it interacts with the serotonin system. But, serotonin gets thrown around in pop science as just a generic, happy chemical.
Oh, and that colloquial definition does such a massive disservice to how complex the serotonergic system really is.
Right.
Serotonin, or 5-hydroxytryptamine, is a deeply conserved neuromodulator. It doesn't just regulate mood, it modulates highly specific neural circuits, including motor pattern generators in the brainstem and spinal cord.
So it's acting more like a traffic cop for neural signals rather than just making you feel good.
Exactly that. When psilocin crosses the blood-brain barrier, it acts as an agonist.
Meaning it binds to the receptors.
Right, it binds to and activates specific serotonin receptors. In mammals, we often talk about the 5-HT2A receptor, which is heavily implicated in cognitive flexibility. But in teleopt fish, The receptor pathways regulating motor output during social stress are incredibly nuanced.
And this is where the evolutionary conservation aspect just blows my mind.
It's wild, isn't it?
It is. You have this molecule that evolved in a fungus. It's synthesized by over 200 species of mushrooms just sitting in the dirt.
Yep.
And by some bizarre twist of evolutionary chemistry, the molecular structure of the psilocin happens to perfectly slot into the serotonin receptors of a vertebrate brain, whether it's a tiny swampfish or a primate.
It really highlights the ancient lineage of these receptor architectures. The fundamental hardware for processing environmental stress and social hierarchy evolved hundreds of millions of years ago.
Long before mammals and fish split off.
Exactly. So when the psilocin binds to these specific receptors in the mangrove rivulus, it's essentially sending an inhibitory signal to the motor cortex, or its equivalent in the fish.
It's basically saying, hey, we see the threat. The visual cortex is processing it, but we are going to suppress the trigger required to launch a kinetic strike.
You are isolating the exact mechanism right there. The serotonergic system is heavily involved in assessing risk versus reward. By modulating those receptors, the psilocin seems to lower the internal threshold for what constitutes a manageable threat.
Oh, I see.
The fish's brain evaluates the intruder, but the serotonin system calculates that the massive metabolic cost of bursting just isn't necessary. It shifts the strategy from active combat to passive monitoring.
It's like snipping the specific wire that leads to the explosion, but leaving the surveillance cameras and the lights on in the building.
It is a profound shift in pharmacological targeting. I mean, proving that a single compound can selectively silence conflict escalation pathways without blunting social cognition. It's a watershed moment for behavioral neuroscience.
It really is. But I want to pump the brakes here for a second, because as with any breakthrough, it's so easy to extrapolate this into science fiction.
We definitely need to check our enthusiasm a bit.
Right, because we are looking at a single study on a very specific species of fish using a single 20-minute exposure. What are the guardrails on this data? What do we still not know?
The limitations are just as important as the findings. As you noted, they used a very brief exposure window. A 20-minute bath only gives us a snapshot of an acute intervention.
It tells us what happens right away.
Yes. It tells us the immediate aftermath.
But it tells us absolutely nothing about long-term efficacy, right?
Yeah.
Or how the brain adapts over time.
Precisely. The way psilocin interacts with serotonin receptors often leads to rapid receptor downregulation.
Meaning the brain realizes it's getting flooded with this chemical and starts, like, removing receptors to balance itself out.
Exactly. It builds tolerance. The obvious future frontier for this research is sustained exposure.
What happens if they get it every day?
Right. If a mangrove rivulus is exposed to low doses daily for a month, does the dampening of aggression hold? Or does the nervous system just recalibrate and revert right back to bursting? We just don't have that data yet.
And there is still a massive black box regarding the specific neural circuitry, isn't there?
Oh, huge.
We know the drug enters the system, we know it binds to serotonin receptors, and we can literally watch the behavioral output.
Right.
But we don't actually have the internal wiring diagram of which specific neural bundles are routing these signals.
We are still looking at a macro-level behavioral outcome. The next phase of research will likely require advanced functional imaging to map the exact synapses. Researchers need to answer why the pathways governing the motor-heavy bursting are so sensitive to this modulation, while the pathways governing the frontal displays are completely immune to it.
We know the switch exists, but we haven't mapped the circuitry behind the drywall.
Beautifully put.
I think that's a really crucial distinction for anyone listening. Science is an iterative process. This study isn't handing us the final blueprint.
No, not at all.
It's proving that a blueprint actually exists. It proves that aggressive motor escalation and cognitive social evaluation are not permanently fused together in the vertebrate brain.
They can be chemically uncoupled.
Yes.
And that uncoupling challenges decades of pharmacological dogma. It suggests that we can move beyond the blunt instruments of general sedatives. If we can map how this works in a teleos fish, we gain a foundational understanding of how those same deeply conserved pathways operate in higher-order vertebrates.
So just to synthesize all of this for you listening, researchers took one of the most naturally combative fish on the planet. They exposed it to a microdose of a naturally occurring fungal compound.
A very brief exposure, too.
Right. And they proved that this compound acts as an incredibly precise neurochemical governor. It binds to the serotonin system and specifically turns off the attack behaviors, the bursting, without numbing their normal social communication.
No zombies, no heavy sedation.
Just a targeted de-escalation of kinetic violence,
Yeah.
which is amazing.
It's a masterclass in behavioral experimental design. It really opens the door to understanding aggression not as this monolithic state of being, but as a series of individual modifiable neural circuits.
Which leaves you, listening right now, with a pretty profound concept to mull over.
It definitely changes how you think about your own brain.
It does. Think about that tiny mangrove fish staring through the glass at an intruder, fully aware of the threat, but chemically freed from the biological compulsion to waste its energy on a physical attack.
It's a powerful image.
If nature has already provided a molecule capable of selectively turning off the specific neural pathways for conflict escalation in a vertebrate brain, well, the implications are staggering.
Totally staggering.
Imagine what mapping those exact same serotonergic pathways could mean for the future of neuropharmacology. Imagine what it could mean for our understanding, and perhaps, one day, our ability to therapeutically manage the actual biology of anger itself.